A lot of the safety innovations in Rust is derived from the weaknesses in C and C++ construct that have been identified as the most common source of bugs today. So to learn Rust, one has to learn it from the perspective of C because these safety innovations in Rust pivots on concepts like memory and memory leaks and pointers that are operational in C and C++. So, for example, if you're coming from JavaScript or Python, it will be difficult to appreciate what Rust is trying to do. So I'll open a C code here, and I apologize, but it has to be C because um, again we are dealing with memory safety, and C programming is the source of the memory and safety bugs of the world today, and it is the where the a lot of syntax in Rust is derived from in C. Okay, so as you can see now, if you are not aware of these concepts in C, then it will be difficult for you to appreciate what Rust is trying to achieve. For example, let us consider this ownership rule. So this is a C program we are looking here, and in line 19, S1 holds a RAM address of the variable containing the value hello, what we call a pointer. And then that pointer is assigned to another pointer. So we now have two pointers, S1 and S2, pointing to the RAM area that has the hello value. This block that I highlight here is having two pointers pointing to the same area. And this has been the most common source of bugs in in the world today. So Rust has decided to formalize that for every RAM address, for every pointer that has able to modify the RAM only must have one owner. Here you can see that S1 can modify the value, S2 can also modify, it has two owners. So Rust prohibits this construct where it has two owners. And C doesn't have the concept of ownership. So in C, you can have a lot of pointers pointing to the same location. It is agnostic about this fact. So to program in C, like how Rust enforces such ownership is to you have to manually kill S1 here. Okay? And since you kill S1, you can no longer print F S1. So after assigning S1 to S2, then you set S1 to null, effectively rendering S1 as deleted or deallocated. So in Rust, okay, um, it looks like this. So we have S1 and then we have S2 in line 12. Line 12, after assigning S1 to S2, automatically rendered S1 as unusable or deleted. Whereas in C, we say that we manually set it to null. In Rust, this is what happened. S1 is no longer accessible. Okay, and if you try to access S1 here, and your program will not compile. However, in C, it will compile. So these are two differences. So Rust is very strict in terms of ownership. It asserts that only one owner at S2 is allowed to modify this area. Whereas in C, there are two owners to make sure that only one owner. So make sure S2 is the new owner. We have to kill S1. Now moving to role 2 in terms of immutable borrowing. Okay, here R1 and R2 is allowed in Rust simply because R1 and R2 are read-only references to this area. You cannot alter the contents via R1 or R2. Because of that, R1 and R2 or multiple read-only references is allowed to point to the same location. Okay. Now, if we look at C, equivalent is not quite the same because by default, S3 is mutable. In Rust, it is immutable. It is read-only. In C, it is writable. So in line 28 and 29, we have two references, and we can, in fact, modify the contents of S3 either by R1 or R2. For example, if you R1 and you change to X, or R2 and you change to Y. So we are now having a construct that Rust does not like, wherein two references, R1 and R2, can modify a common location. So to fix this in C, in fact, let us compile it. So if you compile that and it still compiles, but to fix this in C is to use the const keyword. So now that we declare R1 as a const, and if you try to compile it, and we now have the compiler error, which is like preventing us from doing bad practice. So let's delete this since we cannot modify it. And so this line here in C, lines 27, this line here in C is now just like in Rust. We have we are allowed to have two references R1 and R2 for as long as neither of them can modify the the RAM. So in Rust, neither R2 or R1 can modify. Okay. Now let's move on to a line 23. This is a hard-coded string literal which does not exist, which is not in a RAM address but in a read-only data section. And so it is read-only and it cannot be modified. And in the C, equivalent of that is this one. For example, in C, we can try to modify the W here, change it to X, despite this world value is not in RAM. It is in the read-only section, which is cannot be modified. But we try to modify it here. So let's try to build this in C, and we are able to build it successfully. However, when we run it, it's where we encountered the segmentation fault. In Rust, if we do that like that, when we attempt to modify and then we compile it, and we are not able to compile. So contrast this difference. In Rust, we are not able to compile. In C, we are able to compile, but we encounter the error at runtime. So Rust is trying to transfer all errors at compilation. So so that you will not see this error at runtime where it's in production and it's difficult to change. So if the error is detectable in compilation, then that's a good idea, right? So we cannot do that. In C, there's a fix to this, okay, by declaring const here. By putting const here and trying to change the value of that location, then let's build, and we approximated or we have a similar Rust compilation error. So you can see that you can make you can make C more behave like Rust, but there's a lot of there's a lot of things that you have to be careful, like put the const here. Whereas in Rust, it is the default behavior. So all of this stuff, the intention is to cause the error to be detected at compilation rather than at runtime. We transfer the error at compilation. So this is the reason why a lot of programmers trying to learn Rust is having stress of not being able to compile the program, but it's for your own good because if Rust will allow you to compile the program, then you will later on debug the error at runtime, which is what C is, what you have in C. So there should be a shift in perspective that a compilation error is good for you. Now, let's move now to the rule tree, which is mutable borrowing. So here in Rust, we declare a variable hey and assign it to s4, which is mutable, and then we declare a reference R3, a reference which is also a mutable reference. Okay. So you can modify the contents here via this reference R3. Here you push a string, so hey, then it's now become hey there. We modify the contents, and just like in the ownership rule, this R3 is the only allowed owner because it can modify. So if line 41 will not compile, even though line 41 is a read only, so mixing a read only reference with a read write reference is not allowed. But two read only is allowed. But if one is read write, then only one owner is allowed. In attempts to create another alias reference, even if read only is not allowed. For as long as R3 is in scope in this block. But after this block, where R3 is no longer in scope, like here in line 45, is where you can now declare a read-only reference, R4, and this is fine. In C, you can see it here, R3. So we are allowed to have two reference, R3 and R4. But we know that this is not allowed in Rust. So you can see now the difference between these two languages. C is more of having a lot of freedoms, yeah, a lot of memory addresses pointing to the same location, like here, R3 and R4 points to the what is being malloc here. You might ask, okay, let's zoom in here. You might ask, what's the problem when this block of code is linear and it is sequential and there's no multi-threading? What could possibly go wrong? There is no race condition. So if you have R3 and you have R4, since there is no multi-threading and there's no race condition, what could possibly go wrong? You are right that this is sequential. What could go wrong is, you see, when you str cut to the memory R3, and if R3 is not big enough for the additional string, the common way for programmers to to do in his pattern is to type s4 equals realloc, right? And then there are a lot of stuff following that. So we are trying to expand the size of S4 from 32, then we are trying to expand it to a bigger space to accommodate for additional string that you want to append. S4 here is a entirely new address. But if you assign it here, so you have R3 pointing to the stale, to the old address before the realloc, and you can see where the problem now. So even in a serial, in a sequential set of instructions, you it's always there's always a chance that this address may be invalid, and that is why we can understand why Rust really insists on a one ownership model, that no two pointers can be pointing to the same area because of these situations. So in this ownership move has have seen its incarnation in modern C programming. I mean C++, having move semantics. But C is more of still does not have no concept of ownership. So now we can see that the appreciation of these nuances in Rust has its origins in the C programming in in the memory leaks and ownerships that is perceived as giving as being the source of bugs in C and C++ programming. Of course, other innovations in Rust, such as functional programming, are entirely different. So this only the safety critical innovations in Rust is anchored on top of trying to improve C and C++. So I believe that one has to really see these problems in C or C++ to for this idea to get a hold into one's understanding. And that is all for this session, and thank you.